Hello students, welcome in the part 9 of this D and F local elements. In the last part we have discussed about the melting and boiling point of transition metals. Before I proceed further, let me ask you one question. You have to tell the transition element which is having lowest melting point and the transition element which is having highest melting point. Okay, so if anybody knows, so the answer is that okay, I'll tell the answer a bit later. Okay, let me tell you the lowest melting point. If you know that the element which is found in liquids at room temperature, that is mercury, and its melting point is minus 38 degrees Celsius. And the highest melting point, I think you know, the substance which is put in the bulb in the form of filament, that is tungsten, and its boiling point, its melting point, not boiling point, its melting point is 33,400 degrees Celsius. So tungsten is the transition metal with highest melting point, and mercury is the transition metal with lowest melting point. Now in the next part we'll discuss about variation in atomic and ionic size, or I can say radii. Now see what variation you find in the atomic or ionic size. Generally decreases along the period. If you move from left to right in the period, so generally their atomic ionic size decreases along the period. Now what is the interesting fact? When you move from 3D to 4D, you see somewhat increase in the atomic size, but on moving 4D to 5D, there is very less increase in the atomic size. And further, when we move from 5D to the 6D series, their size is almost, the curve of their size is almost superimposed on the curve of the size of the 5D series. Now why does this happen? So for that there are two terms given about which we will discuss. Lengthened contraction. Due to this, the size of 5D is almost, not exact but almost similar to 4D series. And another term is actinoid contraction, and because of that, and that is stronger than lengthened contraction, and because of that size of 6D series is almost superimposed on size of the 5D series. Now let's see one graph. Here it is, the red one, the green one you can say is 3D series, the blue one is 4D series, and the red one is 5D series. You see in 3D series there is a remarkable difference between the size on 3D and 4D. But if you compare size of 4D series and 5D series, almost nearby. But what happens when we move from 5D to 6D? Then size of the 6D is almost superimposed on the, it is the size of 6D. It will be almost superimposed on the curve. The curve will almost superimpose on the curve of the previous group, that is 5D. So now this is due to actinide contraction, and here the similarity between 4D and 5D, that is due to, here it is due to lanthanide contraction. Now why does this happen? As we know that in D subcell has poor shielding, and the poorest shielding, is due to the F subcell. Now F subcell having poor shielding further, even more poor than D subcell. Now see, in transition elements what happens, as we proceed further, if this is the nucleus, as we proceed further, now this is n minus 1 and this is n subcell. So in what happens in D subcell, as we proceed further, the electrons are added in the D subcell, and D subcell is always penultimate, that is n minus 1. As the electrons being added progressively in D subcell, more and more proton will be added there in the nucleus as well, and because of this nucleus becomes stronger and stronger, more and more positive charge increases. But this inner subcell, which is having D subcell, it does not have proper shielding to the outermost cell, so that there should be an impact on the size. In fact, D is having very poor shielding. The electron in D subcell is having poor shielding for each other as well as for the outermost cell, and because of that the size, actually it should be there, but the size is shrunken and it gets somewhat lesser volume. Because of that, you will see as we proceed further there is horizontal similarity, and when we move from one to next, what should be the size? If 3D is here, 4D should be here, 5D should be here, but in fact what happens, this 4D is very less away from the 3D, and in fact the next, that is almost touching to the previous one, and the next one 6D will superimpose on the 5D. This is due to the poor shielding of the D subcell electron. And one more thing, what happens as we move here, here are the lanthanoids. So before the next element of D D block comes, there are 14 members here of the lanthanides. They are filled progressively. It means here I can say after 5D1 4s2